Okay, I want to go through the derivation of the equation of the ellipse, which is the first part of our new topic on conics. But I want to go over a few points first. So here we have some ellipses, and I want to quickly go over some definitions again. So remember our definition of these conics now all are based on eccentricity. And the eccentricity is the distance from a point on whatever conic it is, and in this case it's an ellipse. So any point P, the locus of P, such that PS, which is a focus, the distance to the focus, or a point, a set point, to PM, which is a line, gives us the eccentricity. Now the definition of an ellipse is that PS, or that the eccentricity, is less than 1. The eccentricity is less than 1. So an ellipse has an eccentricity of less than 1. And it's pretty obvious there. You can see that PS is less on, PS on PM will be a fraction less than 1. Now, that's going to be our definition for all our conics now. And the only other thing we need to be aware of is that when we talk about an ellipse, that distance is a semi-minor axis, and that's B. And this distance is a semi-major axis, and that's the distance A. Now, if A is bigger than B over here, it's pretty obvious we get that sort of ellipse. But if B is bigger than A, if B ends up being the semi-major axis, we get an ellipse going in the other direction. So that's pretty easy for our starting point. So there's our idea that an ellipse, this new conic that we're dealing with, the eccentricity, which is the ratio of any point to the focus, from that point to the directrix, the eccentricity is less than 1. So what we want to try and do is find the equation of the directrix and the focus. That's our aim. So we're going to use some things that we know now. So let's start. Well, we know that the eccentricity is PS on PM. We just talked about that. The eccentricity is PS on PM. Now, that P is an arbitrary point. Let's take a point that is not arbitrary, that we want to discuss or talk about. So let's take this distance here. Let's take this point here, A. That's a point A there. Now, that should hold as well. So AS, and this is not to scale, on A to that point. Well, let's give that a letter as well. Let's call that Z. AS to AZ should be the same. It should have the same eccentricity. So the eccentricity also is AS to AZ. And as a consequence of that, E times AZ equals AS. We're going to use that in a minute. Well, let's take another arbitrary point. Let's take this point over here, which is A dash. Well, by the same definition, the eccentricity, this distance, A to S, should be the same as A to Z, or A dash to Z, sorry. So A dash S on A dash Z. And then we'll get the same thing over here if we multiply that A dash Z across. So E times A dash Z equals, I'm going to put dashes in my Z's so I don't get confused with the 2, because the 2 is coming up, equals A dash S. Okay, so here we go. Now, we know that SA plus SA dash equals, so let's have a look at that. SA is that distance, and that's SA dash plus SA is all the way across. And we know that halfway across is A, so all the way across will be 2A. So SA plus SA dash is 2A. And also, let's have a look at SA dash minus SA. Well, SA dash minus SA, how can we get something from that? Oh, look up here. There's SA and there's SA dash. So SA dash is E times A dash Z minus E times AZ. Well, we'll factorise out the E's and we'll get A dash Z minus AZ. Well, let's have a look at that. What is A dash Z minus AZ? So if we have a look at it here, we're going to get, I'll just get a different colour. We're going to get, here we go, A dash Z is all the way to there, and AZ is all the way there. Oh, so the bit left when I subtract them will be just from there to there. It'll be from A to AZ. Well, that's okay. So we go back to this. E equals A to A dash, which is, we already said, 2A. The distance from there to there. So SA dash minus SA equals that. Now, we're going to call that equation number, we'll call this equation number 1. I'm going to bring this other equation down here, which is SA plus SA dash, and that equals 2A, and we'll call that equation number 2. Now, if we add those equations, so we'll take 1 plus 2, and if we add those equations, well, and I'm going to rearrange this so it makes it easier, because it doesn't matter which way I add, SA dash plus SA. If I add them, well, the SAs will go, and I'll get 2 SA dash equals 2A. 2A, or E2A, plus 2A. So 2 SA dash equals 2A E plus 1. The 2's will cancel. So SA dash equals A outside it, and I'll just write it the other way, 1 plus E. Now, if I take those two equations and I go equation 2 minus equation number 1, look up here again. Here's where we're looking at. So we're going to do 2 minus 1. So I'll get SA dash minus, that'll go, and I'll get SA minus SA. So I'll get SA minus minus SA equals 2A minus E 2A. Well, that becomes SA plus SA, so I get 2SA. And here, I'll take the 2A out again, and I get 1 minus E. I'll divide by the 2, and I'll get SA equals A outside of 1 minus E. And these are my two equations now. That one and that one. So, we're almost there now. But let's have a look at what OS is. OS. Now the point O is the origin. So OS. Now OS is going to equal OA minus SA. And that'll give us OS. Watch again. OS, I'll use a different colour. That distance is going to equal that distance minus that distance. All right. So OS equals OA minus SA. Well, OA, that's just the length of the semi-major axis, which is A. And SA, we have here. It's A outside of 1 minus E, so minus A, 1 minus E. And I'll just expand that, A minus minus AE, which will give me AE. And there we now have, because S is the focus, we now know that S is AE and 0, because it lies on the x-axis. And the distance from A, brilliant. So we've got the value for the focus in two constants, E being the eccentricity and A being the semi-major axis. Righto. Let's have a look at OZ, because OZ, remember, Z is this point here, and it's going to give us the equation in the directrix. So let's get rid of these. OZ. Now, OZ is OA plus AZ. That's pretty easy. OZ is OA plus AZ. Now OA, well, that's pretty easy, that's A. And what's AZ? Well, do you remember? Look up here. AZ is up here. All right? So AZ. So remember, and I'll just use a bit of colour, E equals SA on AZ. So AZ equals SA on E. So here plus SA on E. And SA, look back here, here it is, just above, here it is. So we get A plus A, 1 minus E on E. Equals, we'll get a common denominator, AE on E, plus A minus AE on E. Well, the AE's will go, leaving me with A on E. Now, if OZ, remember O is the origin, if OZ is A on E, that gives us the equation of the directrix. So the equation of the directrix, or the coordinates of Z, are A on E and 0, which means the directrix is X equals A on E. Now, I want to go and find the equation, but before I go there, I need to do another neat little bit. So I'm just going to do a side note, and I'm just going to get rid of that and get rid of... Let's see if I can get rid of that. I just want to get rid of that little bit there. Righto. If I zoom in now, and I select all this, I'll get a new copy of it, and I'll put it down here. I didn't really want to go there. That'll do. Righto. So let's have a look at what we know. We know, and I might, I don't know if that's going to go, oh yes, that's going to go. And I don't want. So I'm going to take this point here. And I know that is 0B because it's on the semi-minor axis. And I now know that S is AE and 0. So if I look at that there, that distance there, and if I now look at that distance there, well, I know that my directrix, my eccentricity is PS on PM. And this is my new point P. Well, I know that the distance from here, from my point here, I'm going to call this my point P, my point P there is from B, and I also know, over here, that the X value here is A on E. So this distance, PM, so therefore PM in this case equals A on E. Now what about this distance here? That distance there. I can use Pythagoras. Okay, so PS square, oh well, I'll do the square root, equals the square root all right, of 0, the x value, because remember this is 0b, 0, just using the distance formula, minus AE, all squared, plus the square root of, b minus 0, all squared. Okay, the square root, that's going to give me AE squared plus B squared is PS. So E equals PS on PM. So the square root of AE squared plus B squared all over AE. So we'll multiply that AE across. So A on E, we multiplied it across, times E equals the square root of AE squared plus B squared. The E's will cancel. So I get A equals the square root of AE squared plus B squared. Square both sides. A squared equals AE squared plus B squared. Swap the minus the B squared, minus the AE squared. So you get A squared minus A, and let's just call it A squared E squared now, because we're going to factorise it out. A squared E squared equals B squared. Factorise out the A squared outside of 1 minus E squared equals B squared. And this is what we're going to use later on, because we're going to use the fact that, and we can rewrite this, we can divide the A squared and get B squared on A squared equals 1 minus E squared. So B squared on A squared plus E squared equals 1. And we're going to use that. We're going to use that in a moment. But I wanted to show you where it came from. Think about it, where it came from again. I picked the point P up here. I calculated this distance, PM. It was just AE. I calculated this distance. I used the fact that the eccentricity equaled PS over PM. I did some algebra and I got these two results. So remember that, I'm going to come back to them. Okay, so let's go back up here, which is where we were at. So we've just calculated or found out the coordinates of the focus and the coordinates of the directrix. Okay. So there's a lot of algebra here in this proof. Now PM, let's go back and have a look at what PM is in this original one that we were doing before. So PM, this distance here, equals, well, it's the same as this distance. Let me just put this in. And we'll call that letter D. Yep, that letter D. PM equals the whole distance, OZ, minus OD. Yep, PM equals OZ minus OD. All right, so let's go over here. PM equals OZ minus OD. Okay. All right, now OZ, well, that's easy. That's A on E. We established that here. And OD, well, OD, well, D has the same X value as P. So it's just X. Now we're getting some Cartesian coordinates in here. Remember also that E equals PS over PM. So PS equals E PM. And PS squared, the whole thing, equals E squared PM squared. Righto. So now we're going to use the distance formula. And this is going to give us our Cartesian equation. So, SP, right, the distance from SP, the distance from SP squared, yeah? The distance here, this is what we're looking at. This distance here. Because we've got the equations of S, and we're going to find the distances SP. So, oops, go back to that. SP squared equals, now remember, S has the coordinates, P is xy, that's going to give us our Cartesian values, and S is, here it is, AE and 0. So the distance formula, SP squared equals x minus AE squared plus y minus 0 squared. But look here, we also know that SP squared or PS squared is E squared PM squared. So we'll put that in as well. So E squared PM squared. Let's expand this. We'll get x squared minus 2AEX plus A squared E squared plus Y squared. We also know that PM equals that. So let's put that in. So E squared, I'm just working the left-hand side now, is A on E minus X squared equals x squared minus 2AEX plus A squared E squared plus Y squared. Now look at this. We have an algebraic expression with E's and A's and X's and Y's, which is a Cartesian expression for the ellipse. We just need to tidy it up. Well, E squared, we're going to get A squared on E squared minus 2A on E X plus X squared equals x squared minus 2AEX plus A squared E squared plus Y squared. Expand through, the E squared will cancel there, so I'm just going to get A squared minus 2AEX plus E squared X squared equals x squared minus 2AEX plus A squared E squared plus Y squared. Righto, let's get rid of the 2AEX. They cancel out on both sides. Let's take everything with x and y to the left-hand side and everything that's just a constant over to the other side. Or bring it all over, bring all the x's and y's over here. So I'm going to move that over to the other side, and I'm going to move that back to the other side. So I'm going to get here a squared minus a squared e squared, and on this side I'm going to get x squared minus e squared x squared plus my y squared. All right, let's factorise out the a squared, 1 minus e squared, and let's factor out the x squared, 1 minus e squared. It's looking a little bit tidier now. Now here's the trick. I'm going to divide everything by a squared 1 minus e squared. Now on the left-hand side, I'm going to get 1. But over here, I'm going to get x squared 1 minus e squared all over a squared 1 minus e squared. And here, I'm going to get y squared on a squared 1 minus e squared. Okay, so 1 equals, watch this, 1 minus e squareds go, and I get x squared on a squared. It's going to be pretty tricky to try and simplify this. But luckily, look over here to what we did earlier. Ooh, b squared equals a squared outside of 1 minus e squared. Oh, that makes that really easy now, because my y is just going to become y squared, and all of that, this bit here, let's use a different, all of this is b squared. And there you have it. The equation of an ellipse, x squared on a squared plus y squared on b squared equals 1. Now, that's what I wanted you to see. Remember, exercise 6A, all questions, and good luck.